All right, so picking up where we left off, we had this little graph of a little circle, a tiny little circle, and as we were pointing out, it traced out all the way around, which normally on a unit circle is 2 pi. It did it from 0 to pi, and the diameter ended up being 1. It was in terms of cosine, and so it ended up having x-axis or polar axis symmetry. Now, what would happen if we traced it out from pi to 2 pi? What would happen? Well, let's see. Will it give us the same shape, or will it give us a different shape? Let's go to the calculator. I want to show you how to use your calculator now. If you go to mode, and this time scroll down, go past parametric to the next one, which is polar. Now you're in polar mode, right? Go to y equals and look what shows up now. You have r equals instead of y equals. Go ahead and type in cosine of, where do you get theta? You hit the X button, and now in polar mode, it's theta. It's your independent variable. Go to your window, and just like in parametrics, you have kind of a theta parameter. Because it's still graphing it on the xy plane, you can still say x min, x max, but your theta now, notice default is 0 to 2 pi. If you want to slow down the graph, you could do kind of the same thing. Let's do 0.03. That'll work. And let's go ahead and do x min, like, how about -5 to 5? And then our y min, y max, let's go -4 to 4. So that's not a, remember the x-axis is a little bit wider. So if I do this, watch as it traces out. Look where it starts, and it's going from 0 to 2 pi. We only went from 0 to pi. Did you see what happened as it went from pi to 2 pi? It traced over itself. Yeah, you could slow it down even more. How about 0.05? Let's see what that does. So here it is. It's going all the way around. There's pi. And now from pi to 2 pi, it's just tracing out again. So it'll continue to do that. So this will always be a circle with a diameter of 1 that traces out once from 0 to pi. If you hit the trace button, notice you can actually click to the right, and almost like parametrics, it's going to count now by increasing theta. So you're actually going to be moving up and to the left, but you get all these, bless you, x and y rectangular coordinates as you rotate through. Now, there is a way that you can figure out what the polar coordinates are as you rotate. If you go to Format, second zoom, you can go rectangular grid. You can go over to polar grid. Now look what happens if you hit graph. You hit trace, and now it's going to give you the radius in terms of theta. All right? And so now you can see the radius decreasing as we approach pi halves, which is 1.57, blah, blah, blah. So you can actually tell the calculator to do a couple different things there. If you're in polar form, if you hit second trace, your calculate menu, you can find dy dx, which will still give you the slope of the tangent line. But you can also figure out dr d theta, which will tell you how fast the graph is moving away from or towards the origin, the pole, with respect to theta. Okay, because that's what r is. It's the distance from the pole. So anyway, let's go back to the notes. And can you imagine what this graph might look like? The a value in front is 2. So if we were to graph it, we would start at 0. Cosine of 0 is 1 times 2 is 2. So it would start over here at 2, and then it would rotate around from 0 to 2 pi, or 0 to pi, sorry. It would make a full rotation. So it's another circle with x-axis symmetry, but the what is 2, Ms. Casper? Not the radius, but the diameter. So the diameter is going to equal the number in front. 3 cosine of theta. Guess what it's going to look like? Right. It's going to trace out once from 0 to pi, and it's going to have a diameter of 3. And because it has cosine, it's going to have x-axis symmetry. Cosine is x. X-axis symmetry, polar axis symmetry, same thing. All right, what if I have -3 cosine of theta? That was a good sound. What's that mean? Yeah, if you pick 0 for theta and you're pointing due east, cosine of 0 is 1 times -3 is -3. So you would retreat in the negative direction. So you're actually starting over there. And then it's going to trace out like this. So there is a sense of direction as well. This one traces out counterclockwise still from 0 to pi. The diameter is still 3, but notice because it's negative cosine, it's symmetric with respect to the negative x-axis, okay? So positive cosine with respect to the positive x-axis, negative cosine symmetry with respect to the negative x-axis. All right, how about this one? R sine of theta. What do you think this one will look like? Well, first one, let's just go ahead and plot it. Let's point due east when theta equals 0. What's sine of 0? 0. So actually, I start at the pole, right? The radius is 0. Let's rotate up here to pi 6 now, because pi 6 is the nice angle for sine. I'm pointing in the direction of pi 6. What's sine of pi 6? A half. So I'm going to be about halfway out. And then if I rotate straight up to pi halves, due north, what's sine of pi halves? 1. And then I come all the way over here to 5 pi 6. What's sine of 5 pi 6? Still 1/2. Good. So I'm right there. And then if I rotate all the way to pi, facing due west, what's sine of pi? 0. I have once again come around full circle. So this is going to trace out like this. It's another circle that traces out still from 0 to pi. But now because it has sine in it, it has y-axis symmetry, right? Or symmetry with respect to the line theta equals pi halves. You can still call it y-axis symmetry. And what's the diameter? 1. So very similar to the cosine. What do you think 2 sine of theta is going to look like? The diameter is going to be 2. So it still starts at the pole, traces out once from 0 to pi, diameter of 2. 3 sine of theta, same thing, but now the diameter is 3, traces out once from 0 to pi, starts at the pole, ends at the pole. All right? And what do you think negative 3 sine of theta is going to do? It's going to flip it across the x-axis. It's going to trace out like that. So just like with cosine, if it has sine, it's going to have symmetry. But sine is going to have y-axis symmetry if it's positive and negative y-axis symmetry if it's negative. So it says, what do you notice about these graphs? They all end up being circles. So R equals, let's call this D sine of theta, or R equals D cosine of theta. They are all going to end up being circles that are offset from the origin. The diameter of the circle is going to equal D. And of course, if it has sine, it's going to have y-axis symmetry. If it has cosine, it's going to have x-axis symmetry. Now notice how simple these equations are, right? They're pretty simple. Cosine theta, 2 cosine theta. Are these things functions of x? Do they pass the vertical line test? No. So you can already get an idea of the simplicity of these equations that are not even really that elaborate in terms of rectangular. Because if you were to write, let's say we wanted to write the rectangular equation for that. Remember, the equation of a circle is x minus h squared plus y minus k squared equals r squared, where the center is at hk and r equals the radius. Wow. So what would that be? What's our center over here on this one? If the diameter is 2, the center is at 1, 0, right? So the equation would be x minus 1 squared plus y minus 0 or y squared. And what would the radius be if the diameter is 2? 1. So that would be 1 squared. So if I were to solve that for y, first of all, it would require 2 equations, yeah? It'd be y equals plus or minus the square root of 1 minus x minus 1 squared. So just to create that simple little graph in rectangular form would require 2 equations, both with an ugly radical, whereas in polar form, it's just the cute little equation r equals 2 cosine theta. So a different representation, more suitable in this case because it's not a function of x. So you do want to kind of memorize these families of polar curves. Okay, so anything of the form r equals plain old sine or cosine with a value in front, that's the diameter. All right, let's look at example 3. If I take the same thing from example 2, but now I add a coefficient in front, or add a constant in front. Yeah, if we were doing rectangular, it would be a vertical shift. But what does it do to the radius? Okay, we're kind of generating the graph a little bit differently. Let's just see what happens, okay? Let's just kind of pick, again, our nice angles. We'll rotate all the way around from 0 to 2 pi. So at 0 on the polar axis, the angle is 0. We're pointing due east. Plug in a 0 for theta. What do you get? Cosine of 0 is 1. So you get times 2 is 2, plus 2 is 4. So we start off over here at 1, 2, 3, 4. We start off right there at 4. All right. The next convenient angle for cosine, as we mentioned, was pi thirds. So if I point up there at 60 degrees, pi thirds, what's cosine of pi thirds? A half. Half of 2? 1. 1 plus 2 is 3. So I'm going to march out 3 units. So 1, 2, 3. It's going to be somewhere right about here. If you imagine this y-intercept of 3 kind of coming down in a circle, approaching here, it's going to be somewhere in there. All right, then we point due north at pi halves. What's cosine of pi halves? 0. And 0 plus 2 is 2. So we're right here. So notice what my radius has done. It has gradually decreased from 4 to 2 as I rotate. All right, so let's keep going. The next convenient angle would be over there at what? 2 pi thirds? What is cosine of 2 pi thirds? Negative 1/2 times 2. Negative 1. What's 2 minus 1? 1. So we're right here. Okay, we go out 1 unit. And now we point due west, which is pi. What's cosine of pi? Negative 1. Times 2? Negative 2. Plus 2 is 0. We hit our first polar 0 there. So if you notice what's happening now is it comes around like that. It kind of looks like the top of either Elvis Presley or Jay Leno's hairdo, right? Kind of like a pompadour, maybe. I don't know. That's what I see. You may see something else. All right, let's go ahead and keep rotating. We haven't really kind of created a loop like we already did at this point on the others, right? We haven't come full circle. So let's work our way back out. Let's come down here to 4 pi thirds. What's cosine of 4 pi thirds? Negative 1/2. Good. Times 2 is negative 1. 2 minus 1 is 1. So we walk out a 1 unit in that direction. So notice this point over here at 2 pi thirds and now at 4 pi thirds, they're symmetric across the x-axis. Point straight down due south at 3 pi halves. What's cosine of 3 pi halves? 0. So we have 0 plus 2 is 2. So we walk down, straight down 2 units. Notice that is symmetrical across the x-axis with the y-intercept up above. We come over here now to 5 pi thirds. What's cosine of 5 pi thirds? Positive 1/2. Times 2 is positive 1. 2 plus 1 is 3. That's going to be symmetric with this point straight across the x-axis. And then we come back around full circle all the way to 2 pi, and we end up with 4 again. So this thing kind of walks back out like this and makes a full loop, a full rotation, not from 0 to pi, but from 0 to 2 pi. How many polar zeros did it have as we went around once? Just once, okay? It comes around and it basically bounces out of the pole with a nice cusp there, bounces out of the pole and comes around. This right here is a very special type of polar curve. If you turn your head 90 degrees to the left and imagine this being red, it looks like a heart. It looks like a heart. If you turn your head 90 degrees to the right, it looks like a butt. So whatever you want to do, whichever way you lean. It's a heart to the left, it's a butt to the right. So most people call it a heart graph. Harley Rogers one year always called it a butt graph. And that's how I remembered it. So that's fine, Harley Rogers. If you're listening, it could still be your butt graph. But a heart doctor is not called a heart doctor. By the way, it's National Doctors Day. What do you call a heart doctor? A cardiologist. So this is called a cardiograph would be good. Cardioid. We call it a cardioid. 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 There's a lot of vowels there. Yeah. Now, if you notice, it has what type of symmetry? X, Y, or origin? X. It also has what trig function in it? Cosine. Is that consistent with what we've seen? Yeah. And because it's a positive cosine, it's plus 2 cosine, the majority of the area is on the positive x-axis. So if you look at it, you could think of this as having a min and a max radius. This would be the max radius, which is 4, and the minimum radius is going to be 0. So if you look at your two numbers, the 2 that's the constant and the 2 that's the coefficient of cosine, what's 2 plus 2? 4. That gives you your maximum radius. What's 2 minus 2? 0. That gives you your minimum radius, okay? So a cardioid comes around, bounces off the pole with a cusp, and bounces back out, okay? Creating the cleft in the heart or the crack in the butt, whatever you want to call it, all right? So that's when the 2's are the same. It could be 3 plus 3 cosine, 4 plus 4 cosine. It's going to be very similar. Now let's look at the next one here. Again, I have two terms, but this time it's 1 plus 2 cosine. These are different numbers. First of all, what type of symmetry do you imagine it'll have? It has x-axis symmetry. Good. Let's go ahead and trace it out. We'll do the same thing. I'm not going to draw them each time. We're going to go a little bit faster. Facing due east when theta is 0, what do I get for my radius? 3. So this one starts at 3. Good. Pointing in 60 degrees at pi thirds, cosine of pi thirds is still a half. Half of 2 is 1. 1 plus 1 is 2. So I'm going to walk out 2 units, which is about right there. Kind of imagine the radial line coming in there. And then due north is pi halves. What's cosine of pi halves? 0 plus 1 is 1. So we're right there. Rotating over here, we have 2 pi thirds. Cosine of 2 pi thirds, negative a half times 2, negative 1. Negative 1 plus 1 is 0. Oh boy. Okay. We have hit a polar 0 now at 2 pi thirds, not at pi. Let's go ahead and rotate down to pi. What's cosine of pi? Negative 1. So I end up with 1 minus 2, which is what? Negative 1, which means now I'm pointing due west and I have to retreat 1 unit. What the heck did this thing just do? Yeah, it came inside itself. It's doing this and it hits the pole, but then it circles back around like that. Now, if you thought the previous pompadour was something, this is one of those overlapping, hanging over, Dunlapping pompadours, right? It's hanging over so far, it's curved back under on itself. So that's at pi. Now let's keep going. If we rotate over there to 4 pi thirds, what's cosine of 4 pi thirds? Negative 1 half. Good. Times 2 is negative 1. Negative 1 plus 1 is 0. So we've come back here and we've hit the pole again. When we're pointing straight down, we're back at 0. Huh? No, this one has a different name. It's a snail. Yeah, very good. It is a snail. That's what it's called. It's called a snail graph. If you work your way back out, pointing due south, what's cosine of 3 pi halves? 0. Plus 1 is 1. So we're going to come straight down here. So we're kind of coming back out of the inner loop. If you come over here to 5 pi thirds, that's positive 1 half. So that's going to be 1 plus 1, that's 2. That's going to be over here. And then you come around full circle to 2 pi, and you end up with 3 again. So this one does make a full rotation from 0 to 2 pi, much like the cardioid previously. But this one doesn't bounce off the pole. This one comes around, goes past the pole, overshoots it, comes back inside of itself, and then traces back out, hits the pole again on the way out, and traces. So this one has 2 polar zeros between 0 and 2 pi. This one is called a snail graph, but it's the French word for snail, which apparently is le snail. I don't know. Do you know what it is? Oh, escargot, I believe, is correct. But apparently it's also limaçon. No, this is, I don't know, it's French. There's like a fish hook on the sea. And that means that it's a soft sea. So not limacon, but limaçon. Okay? And limaçon supposedly means some kind of snail. So somebody thought it was a snail too, not just Zach. This is a limaçon. It's a special cardioid, essentially, that traces inside of itself. Now, let's look at the numbers again. Like we did over here, 2 plus 2 was 4. That was the max radius. 2 minus 2 is 0. It was the minimum radius. Let's see if it works over here. What's 1 plus 2? 3. That was your max radius. And what's 1 minus 2? Negative 1. So that's going to be the inner radius, okay? So this ends up being a limicon. It has an inner loop, and the radius of the inner loop is the difference of the two numbers. The radius of the outer loop is the sum of the two numbers, the absolute value of them. But it is cosine and still have x-axis symmetry. All right, let's look at this one here. This one is very similar, except it's now reversed. Instead of the number and the coefficient being the same, the constant is bigger. Let's see what this one does. Point due east, 0. What's cosine of 0? 1. So we end up with 3. So this one starts at 3 again. Rotate up to pi thirds. You get cosine of pi thirds is a half. What's 2 plus a half? 2.5, right. So 2 point, somewhere right in there. And then straight up at pi halves, we get 2. And then over there at 2 pi thirds, we get negative 1/2. 2 minus a half is 1 1/2, so it's going to be right around there. Point due west at pi, cosine of pi is negative 1. 2 minus 1 is what? 1. That's the closest we ever get to the pole. This thing goes around like this, and that's as close as it gets to the pole. It doesn't hit the pole because they're not the same. It doesn't cancel out to give you 0, and it doesn't go inside of itself on its way through the pole because the constant is bigger. So now if we trace our way back out, guess what's going to happen? It ends up doing the same thing down below. So this one, it's not a perfect circle. It should have x-axis symmetry, and I didn't really do a good job of showing that. That's not much better. It kind of looks like if you set a cantaloupe down on the counter, you know, the gravity will kind of make it a little bit flatter on one side. This one is called a dimpled, a dimpled limicon or a dimpled cardioid. They belong to the same family. Dimpled limicon / dimpled cardioid. But it doesn't actually hit the x-axis or the polar axis. It has no polar zeros. All right? But it does have x-axis symmetry, and it traces out once from 0 to 2 pi. So there you go. You should kind of summarize those now. When the constant and the coefficient are the same number, it's going to bounce off the pole. It's a cardioid. When the coefficient is bigger, magnitude-wise, it's going to have an inner loop. It's a limicon. And when the constant is bigger, it's just going to be kind of flat. It might dimple in there a little bit. Kind of like, maybe it's not even flat. Maybe it does something like this. Comes around, and maybe it kind of acts like it's going to go in, but it doesn't. Maybe like a peach. Right? See, it doesn't hit the pole, but maybe it dimples there. All right. What do you think these guys are going to look like if we just replace cosine with sine, but the numbers are the same? The same thing, but with y-axis symmetry. Good. Now, what's important with polar curves without a calculator is to kind of figure out where they start and where the polar zeros are. You could actually figure out polar zeros in the exact same way you figured out rectangular zeros. You take your equation, you set it equal to 0. But now instead of solving for x, we're solving for theta. Theta. Right? So if you want to find your polar zeros, set the radius equal to 0 and solve. We get 2 sine of theta equals negative 2. So sine of theta would equal negative 1. Now, where is sine equal to negative 1 from the unit circle? At 3 pi halves. So there's only one polar zero within one rotation. So if you want to know how this one traces out, just pick your quadrantal angles now. Let's not mess around with all the interiors. Point due east, that's when sine is 0. What's sine of 0? 0. So we start at 2. We start right there. Pi halves, what's sine of pi halves? 1. So we have 4. We're up here at 1, 2, 3, 4. Over at pi, sine of pi, 0. So we're 2 units out that direction. And of course, 3 pi halves, we have a polar 0. 2 pi, we're back to there. So now you can kind of see that this graph traces out like this. And this is where Harley started calling it the butt graph. Okay? Or you could think of it as a heart that's upside down. All right? So it is a cardioid, just like it would be for cosine, but because it has sine, it has what type of symmetry? Y-axis symmetry. Trace that once from 0 to 2 pi. The maximum radius is still 4. The minimum radius is the difference is still 0. What do you think this guy's going to look like? 1 plus 2. Well, let's figure out where the polar zeros are. Set it equal to 0. You get 2 sine of theta equals -1. Sine of 0 then equals -1/2. There are two angles now on the unit circle where sine is equal to -1/2. What are they? It's your pi 6 reference angle, but it has to be in which two quadrants? 3 and 4. So it should be 7 pi 6 and 11 pi 6. Yeah. So this is going to have two polar zeros, so it's going to be a limison. It's going to have an inner loop and an outer loop, and it hits the pole going in and out. So again, where does it start? Point due east at 0. Sine of 0 is 0. We start at 1. Come up here to pi halves. That's going to be 3. Go over there to pi. Sine of pi is 0, so we're back at 1. And now we know we hit the pole twice and we come back around. So it's going to look like this. And then it's going to hit the pole. And then what's the inner loop? What's the radius of the inner loop? What's 1 minus 2? -1. So it's going to come in 1 unit. You can have any number as long as the constant's bigger. If that were like a 1 plus 4, then your outer loop would be 5 and your inner loop would be 3. This one comes in 1 unit and then comes back out and then finishes up like that. So it still has y-axis symmetry. And then the last one over here, 2 plus 1 sine, guess what that one's going to be? That again is your dimpled limison. You're going to start at 2. You're going to come up here to 3. You're going to go down here to 2. And then it's going to end up coming down here to 1. Maybe it's going to get flat. Maybe it'll have a slight little dimple in there. Kind of looks more like a peach. Call it the peach graph. You don't really have to know the names. What you have to do is be able to sketch the graphs and all that good stuff. Now again, notice, especially with the limison, these things fail the vertical line test pretty badly, right? So I can't even imagine what type of rectangular equation that's going to be. It would require probably several. But the polar equation, 1 plus 2 cosine theta, relatively simple looking. So polar curves do a much better job of handling elaborate curves. And there are some very, very pretty polar curves. If you go to polar mode and you start just playing with trig functions and typing in different values of theta, you can get some things that trace out to be just unimaginatively beautiful. You might waste the evening looking at pretty things, especially if you have one of those new fancy colored TI-84s. All right, so we'll stop right there. Tomorrow we're going to go a little bit more quickly. We're going to meet a couple of other functions. We're going to start doing some conversions, and then we're going to bust out the calculus, all right? BOTC.